say something here? Or should I just go?
Oh. Today we have such a distinguished speaker that I have to actually introduce the introducer. So we have here the privilege of having, Sanjeev Singh, Professor of Robotics, and now the CEO of Near Earth, and many other companies, I believe. And Sanjeev has done a lot of field robotic stuff. Of course, robots flying, underwater, on the lawn, and everything else. So I'll let Sanjeev introduce the speaker.
Thank you. What a great introduction. Yeah, I'll be the cover act. So before we go any further, I was told to let everybody know there is a post-seminar reception in the Robo Lounge. If you don't know where the Robo Lounge is, then that's your job to figure it out where all the good food is. And we hope to see you what time? Right after this? Okay, good. So it gives me great pleasure. Katrina asked me, she said, hey, you've been around here, since Carnegie Mellon was being formed or something like that. So do you know Herman? And so I immediately responded to her saying yes. And Herman and I go way back, and specifically, we were classmates together, and then office mates together, and then we started one company together. So yes, of course, I do have a lot of interesting anecdotes. So I was trying to think about what I could sort of say. Herman's a mild-mannered guy. He didn't sort of jump the fence and steal some soldering iron or anything else like this. So what am I going to tell you? But one thing is, I asked Herman about how he got his name. It's kind of a curious name. He's like, this is a typical Herman response, right? It is a very simple thing. When I came to America, they asked me, what's my first name? I said, Herman. And then they said, what's my last name? I said, it's Herman. He comes from a country where they only have one name. So he just said, he has too much trouble trying to explain this as and Herman. So here you are.
Yeah.
So that's the only thing I could think of that I could say in public anyway. Anyway, there will be many great stories one day when we write our memoirs. There's more coming. Okay. So in any case, when we were grad students together, one of the things about Herman that I noticed was he was like the smartest person I knew. Like, he could talk about anything. If you wanted to ask about hardware graphics, or if you wanted to talk about imaging, or if you wanted to talk about radio comms, or like how embedded computing worked, like just about anything you could think of, you go to Herman and he would have the answer, right? So he's been if you read his bio, he's been doing all sorts of stuff, and really cool stuff, some of which the two of us actually were when that building was still being built. It was actually an abandoned building, and it was so abandoned that we had to actually put like a trailer inside there, and that was our office. And then there were trailers outside this building. Now, of course, it's a great building. So Herman and I were at the onset of the National Robotics Engineering Center in the late 90s, and a few years ago, Herman stepped up and he has taken the leadership role at the NREC. And if you guys don't know, because you're new to robotics or new to Carnegie Mellon anyway, Enric is the entity that does the big stuff at Carnegie Mellon in terms of robotics going out into the industry. They're clearly recognized as a leader in this area of commercializing and doing very large, notable things. If you watch the DARPA Robotics Challenge with humanoids, that would be a thing that the NREC did. There were many other very large projects, and of course he's going to tell you all about them. And so that's what they did, and they continue to sort of not only set the stage, it was like our first foray, big foray into commercialization. And what I can tell you is as I go around the country and even to other countries, people know about the NREC now. They associate that with with Carnegie Mellon, and there are even places that were inspired by NREC. Like, for example, Pennovation at UPenn. When I was there a few months ago, they said, well, we came to NREC, we saw this, and this is our version of NREC. So I think that's a recognition of how far this experiment has gone, and I'm very curious to find out after so many years what Herman's learned. So I'm here. Please welcome Herman Herman.
Sounds good. Thank you, Sanjeev. Okay. Thank you all for coming So today, I'm going to talk a little bit about NREC, about some of the lessons learned. I've been doing robotics for quite many years, building quite many systems, deploying quite many systems. So we go over, again, some of the lessons learned from all those things. And also some musing on where do we go from here in the robotics area, okay? Since many of you are probably not familiar with NREC, I have a few slides here to describe what we do, okay? So NREC was created back in 1996 by Carnegie Mellon University, right? Even back then, we can start seeing the demand for applied R&D center, okay? So a few people have the vision to create this thing, Red Whittaker, Rats Reddy, Takeo Kanade, the provost back then, Paul Cristiano, and the president Marabian, basically make this thing happen, okay? So we've been around for about 21 years. We are a semi-independent business unit of the Robotics Institute. We are also fully funded by our client. So all our funding comes from our sponsors. And right now, about half of them are commercial companies and half of them are government entities, right? And this is a big change from where we start. So when we started 20 years ago, about 90% of all our funding come from government agencies, DARPA, DOD, DOE, right? And over time, we've been doing more and more commercial product development. And this shows the sign of maturation for robotics technology. More and more of them are ready to be commercialized into a product, right? So we are one-stop shop for robot development. We have hardware engineer, software engineer, system integrator, all those things, right? So some interesting factoids, we have business in 5 continents. So we have client and sponsor certainly in US, South America, Africa, Europe, Asia, Australia. So we do work around the world, actually. We also created multiple spin-off company. When a project ends, sometimes there's a demand from the sponsor, from the market to create the company. So we do that as well. Another interesting fact is that building you see here in the background, this is about 120 years old building. Originally, it was a pipe factory, Epping pipe factory, where they make all the piping for the first US nuclear submarine, USS Nautilus. So the building has a great history, and we are happy to be in this building. Okay. So anyway, some pictures from the old days. This is pictures rendering from about 20 years ago. Okay. So back in 1995, it's all just a dream. There's this really, really old building, abandoned building in Lawrenceville. And people say, hey, why don't we turn this into state-of-the-art robotics R&D facility, right? And the rest is history. So, and we built the building. So that's what it looks like back then. We tear down most of the shell and keep the structure, basically, right? Now, it's a very nice facility. And one thing we are proud of, we're not saying this all happened because of us only, but certainly we play a critical role. Lawrenceville now is becoming one of the most desirable places to live in the whole city of Pittsburgh, right? There are a lot of nice property there. And part of this because there are many companies, high-tech companies, start up around our facility, okay? So once we are there, people start building another facility, company moving in. As company moving in, there are a lot of great jobs. People need a place to live. So they are building apartment condos also, right? So now, the whole neighborhood is transformed, and we are very, very happy to play a role in that. So right now, what is happening is, I like to call the robotics triangle. So, with NREC here on the north edge of the triangle, Carnegie Mellon on the southeast and downtown on the southwest, there are so many different high-tech companies, not just robotics, okay, including startup from CMU and other universities as well. But there's a huge concentration here in this triangle, and we are happy to be part of this. And if you look further, sort of a long, long time ago, right? There's a long history of robot and robot development. One of the first sort of robot that developed in Pittsburgh area is back in 1927. There's a guy named Roy Wensley at Westinghouse Electric that built that things that look like a robot. It's actually just an automated phone answering machine, right? But given the limitation back then, relay, tube. It's amazing what it can do. It can answer the phone, understand very simple word just by frequency discrimination, and do some playback, right? So the history of doing robot in Pittsburgh go a long way. Okay. Now we basically built various robotic systems for companies and government. Like a couple examples here. The upper left-hand corner is the robot we built for Shell Oil. It just passed all the qualification tests recently, so it's being deployed in Kazakhstan, oil refinery, right? The qualification test is about 100 pages long. Before you can send any equipment to an oil refinery, you need to make sure it doesn't blow up, things like that, okay? So that's a commercial success. We also develop a lot of stuff for defense. You could see the 6-wheel hybrid electric vehicle there, okay? But we also do things like sensor development. So for example, this is a simple system we developed for humanitarian demining. Okay? So we built quite many of these things. They are doing mine clearing, UXO clearing in Cambodia, Angola, Laos, to find all the unexploded explosive leftover from the war, right? So we do a full gamut of product development. A few other examples. The yellow robot and the blue robots are mining robots we developed from clients in South Africa. Basically, when you think about natural resources, precious metal, gold, platinum, all the easy to mine places are gone. So all those things can only be found by going deeper and deeper into the earth. And it's very hard to send human there, right? So they're looking into robot to solve some of their problems. And sometimes we supply technology to other companies. You are probably familiar with Big Dog from Boston Dynamics here on the right side. So for that, we supply all the sensing technology and all the perception technology to allow that robot to walk autonomously. Okay. So I will show a quick video here, just showing what we built. So we have activity in autonomous farm equipment. This is one of the early machines we built. This is a project that Sanjeev and I work together, a fully autonomous excavator for Caterpillar. Okay. So one of the interesting points is, by the end of this project, this is a successful project from technical standpoint, but back then it's so expensive to replicate. It just doesn't make commercial sense. Technically interesting, but back then it's just so expensive. We ended up having to design our own semi-custom laser scanner, millimeter wave radar, and all those things. Okay. But this is actually one of the first projects run at Enric, right? Yeah. So that is one of the early prototypes for Crusher, the 6-wheel, okay? With the autonomous helicopter flying off it to do mapping in front of it. Okay. And then one thing that differentiates us, since we tend to build mature stuff, we spend a lot of effort on testing. A lot of effort testing. I will say more about that. Right? This is just time-lapse video to show the building. This is a gas pipe inspection robot that is licensed by a gas company to do live inspection on live gas pipe. Okay. So that's an autonomous forklift assist and system there. Okay. So you could see, even back then, all these videos, some of them are 15, 17, 18 years old, right? Even back then, from technical perspective, many things could be done. They're just too expensive to be deployed as a product. And that is one of the big changes here in the past couple of years. Suddenly, the cost of doing all these things is much, much lower. Right? This is another 6-wheel vehicle we designed for the Marine. Okay. That is Crusher. Okay. So this can drive by itself. This video doesn't show the sensor, but there's a version of this that also drives by itself pretty well. So one thing is when you're testing robot like this, it's pretty fun actually, to see all these things. You can destroy cars, you can run over cars, you can do all crazy stuff. So that way it gets its name, right? Then again, we have a lot of activity on the commercial space. This is a fully autonomous tractor we developed for John Deere. We built 6 of these things. It can do mowing, it can do spraying, it can do quite a lot of stuff. It was tested in Florida. We have quite many miles, autonomous miles on this thing. And not only that, when we test this thing, we have the farmer themselves operate the tractor. Okay? It's one thing to build something that engineer can operate. It's another thing to build something that a non-technical people can operate. Much, much harder. Okay? So again, so this is a good example of something that technically pretty mature. Again, we built 6 of these things. But at the end of the program, John Deere wasn't ready to introduce it as a product yet for non-technical reason. Right? They worried about liability. They worried about all the other issues, not from technical perspective. Okay. That's the yellow robot that we built for Shell Oil. Basically, it would go around and do inspection and do gas detection, especially hydrogen sulfide. One whiff of that, if there's a leakage, enough to kill somebody. In fact, in Houston, leak just killed 2 people. You cannot smell it. By the time you look at it, it's. I will show more of this video later on. Let me fast forward. Okay. This is also another interesting thing. When you're testing robots, there are many, many incidents. That's what makes it interesting. I just say that. We damage a lot of stuff. This is one of our early prototype for a self-driving vehicle. Right? Still lots of bugs. Sometimes you look back and say, how can it not see something? Basically, it cannot see the negative obstacle. So it's there. It's there. Just the sensor doesn't go down far enough, so it cannot see it. Right? It's obvious, but in hindsight. Okay. So then again, later, this is about 2 years ago. That is our entry. You guys might seen some of this video. That's Chim. Okay. So the distinction for Chim is we didn't get the first place in this competition, but we are the only robot. Chim is the only robot that can recover after it fell down by itself. Okay. So right now, what we're doing with Chim is the robot itself is too complex for commercial application. So instead, there are many technology that is incorporated in Chim that we are incorporating in other products we are developing for a few companies. The manipulator technology, the sensing technology. So we have a couple programs right now that basically take technology developed for Chim and applying it to this new set of applications. So that's a unique way. That's the safest way for us to go, for Chim to go up the stair. So that was the biggest relief when actually it gets up, get up there and finish the competition here. So anyway, so what differentiates us is, usually university do basic research, right? You develop technology, you develop algorithm that do amazing things, right? So what's unique about NREC is we take basic research all the way to pretty much production prototype, okay? And a good example of that is this fully automated laser paint stripping robot. This is probably one of the most complex robots we ever developed, okay? It took us about 4 years. Okay. It started with a very small project, and in the end, we produced 6 production quality robot. Okay. We also do that for other commercial customers. We even got the Supplier Innovation Award from John Deere, which is the largest equipment manufacturer in agriculture, right? Because we just produce so much technology for them. So for this robot, I'm going to use this as an example of what you can do in robotics right now. This is a very complex robotic system, aircraft coating removal system. The Air Force has been trying to solve this problem for 20 years. They worked with few companies before they worked with us, okay? And they didn't get what they want, okay? So basically what they want to do is they have about 3,000 aircraft in their inventory. Every 3-4 years, they need to be stripped from paint and repainted. Otherwise, they will rust and have damages, okay? So they want to have a fully automated system to do this, because otherwise, for one aircraft, it might take them 2 weeks to strip the paint off an aircraft, right? So we start this with a very small project, just 150K, okay? They said, hey, can you solve this thing? So we have a very small project. We develop a concept. They look at the concept. It looks great. Why don't you guys build it, okay? So we built the first unit 1 year later, and it works pretty well. I will show you the picture. We even have a full F-16 in our building. Okay, so our building is big enough. We remove the wing, we bring in the airplane inside, assemble the wing, and we use it for development. So this is inside our building, right? And that is the first prototype of the robotic system. Okay, it works well, and they said, well, why don't you guys build a fleet of these things? So we end up building 6 of these. They are all installed in Air Force Base in Utah, Salt Lake City. Okay, so you can see this robot working on actual production Air Force aircraft. Okay, so the scary thing about this is if you make a mistake, if the robot make a mistake, that aircraft costs about $40–50 million. So you just go in $40–50 million aircraft. Okay, the laser there, if you just linger for half a second too long, it basically will drill a hole to the whole aircraft. Okay. That's why there's a triple safety redundant system there. Okay. So this is one of the most complex projects that I led. It's very satisfying also because it ends very successfully. Okay. So you notice in addition to stripping the airplane, it also built a very accurate as-built model of the aircraft. Okay. And this is one of the key to make the system work. All the previous effort, all the other companies that try to solve this thing, they use the CAD model from the manufacturer, which turns out is completely different with the actual shape of the aircraft. So you take 2 aircraft, they are not the same, right? So instead of that, we map it in 3D. We use that real-time data to control the arm and do that pretty accurately. So. And at the end of this project, the Air Force want more support. We also want to see if we can deploy this for commercial aircraft like the Boeing 737, Airbus 320. So we spin off a company, Titan Robotics, which is doing pretty good right now, trying to push this technology out there. Right? Another benefit that might not be obvious is, if you look at the room, it's very clean, right? There is no debris, there is no paint debris or anything. Because there's a suction mechanism, there's a vacuum mechanism that sucks all the debris, the paint that is removed by the laser, and there's a HEPA filter on the other side that filters that. So at the end of the process, you got a box, a container of dry paint. It's a very, very clean process. Okay. Okay. So hopefully that gives you some context about what we do, the type of equipment that we develop. Okay, so developing all these different systems, working with different companies, some of them startups, some of them big companies. We do learn a few things. Okay, some of these lessons are hopefully useful for all of you guys that might be developing new systems, startup a company. Okay, for example, many systems we built, right? We start with the project, and it's obvious one is the hard problem is, right? But one thing that people keep underestimating usually is they usually neglect the simple things that need to be done to make the whole system work. in addition to that one hard problem, right? That thing can occupy 50–80% of the effort. But people just don't think about it because they said, well, it's straightforward, right? Like calibration, okay? Calibration is not technically difficult, but it just takes time to do well, right? And if you don't pay attention to that, you won't have a good product, okay? So this is pretty critical to differentiate. Do not confuse something that technically is simple with small amount of effort. You know? Something could be simple, but still require a lot of effort there, okay? Another thing is people ask us, you know, the robot we build tend to be reliable, tend to be, especially the production prototype, right? And I think one of our secrets is we have good technician and machinists and fabricator. You know, do not underestimate the value of quality work. When you're putting cable, you're putting stuff. It's not as sexy as engineer work, but hey, they are equally important. You know, if not more important there. In the end, you know, technology keep moving, right? But like people said, it's people, and people. It's in the end, regardless of what system we develop, you know, good engineering with dedicated engineer produce great result because you will have problems, right? Different product, different development looks different at a high level, but when you get down to it, the type of problem, the type of issue you encounter tend to be the same type, and you know, dedicated people usually can work through them and produce excellent results in the end. Okay. Another thing that we notice is as the robot that we build get more and more capable and complex, the portion of the effort that we spend on testing is increasing significantly in terms of percentage. Right. So let's say you got $10 million to develop robotic system. If it's a simple robot, you might spend $7 million for development, $2 million for testing, $1 million for other stuff, right? As the robot gets more complex, you might need to spend $4 million for development, and you might spend $5 million for testing. Okay, this is a real issue as robot getting more and more complex because we have high-dimensional input. For example, for self-driving car. Just the type of environment, you know, city of Pittsburgh, San Francisco, Washington, D.C., they're all different, right? In Pittsburgh, we don't have 6-lane highway, okay? So we don't have the scale to test thousands of autonomous cars, 6-lane highway going in this direction, right? But in Washington, D.C., if you could imagine in iPhone 495, you have 6-lane highway going in one direction, the other one going in the other direction. So if all those cars might have laser, you know, shining each other with the laser beam, you might have scalability issue, for example, right? So high-dimensional input, sensitivity to calibration, okay? If you just have a demonstration project, you make it work, you calibrate the robot, it works well for 1, 2, 3 days. If you're designing a product, guess what? That's not enough. 1 year from now, it still needs to work. And that is a big issue, actually. It's very hard to build something that maintains calibration. If you use machine learning, as you guys know, it's somewhat non-deterministic with regard to the stimulus, because if you say something new, you're not 100% sure how it will react, right? That makes it also challenging. Okay? In the end, it's just challenging because it's an adaptive system. The robot reacts to the environment. And as we know, the environment that we all live in is very, very extremely complex. So because of that, you know, if you guys want to build reliable robot, just don't undercut or underestimate the need for testing. Testing. It's directly correlated to how well that robot will behave. Okay. Few other observations. Okay. It's critical when we design a robot, okay, to get that prototype out there in the customer side. Okay. Many times a company would come to us, a client would come to us, hey, can you design a robot to solve this problem? And they said, and we asked them, okay, what is the problem? The problem is A, B, and C, right? Okay, so we built the robot to do A, B, and C, and we get the robot out to that site, you know. Only to find out the problem is not A, B, and C. Those things are easy, actually. The problem is D, E, and F. Many times people don't even know the right problem to actually solve. And you don't find that out until you actually get the machine, the robot out there. Okay. A good example of that is the right user interface, right? If you don't have the right user interface, you can build the nicest robot you ever built, and everybody will hate that robot. Okay. Now, on the other hand, when you start deploying multiple units, sometimes when we build prototypes, sometimes we have a dozen or 2 dozen of those machines out there. Okay. And if you do this too early, then you also have a problem. Okay. Because let's say you build 100 robots, right, with 99% uptime. So it can operate with 99% reliability. If you have 100 prototypes, that means is on average, one of them is not working at any time. Okay. So if you do that too early and the prototype is not mature yet, what you end up doing is you're occupying your whole development team handling those issues in the field. You got that phone call at night, you got that phone call in the weekend saying, hey, something is not working, something is not working. And basically, you just kill your developer. Okay? So it's important to balance early testing for 1 or 2 robots out there in the real environment, but not doing testing in the field too early when you're starting amplifying the number of machines out there. I know this affects many startups also. I saw some of them do quantity deployment too fast. Then they got bogged down because they got so much data they cannot handle, so much bug report they cannot handle anyway. So what's the purpose? Right? So there need to be a balance here. There need to be a balance here. Okay. Another thing we notice is more and more of the problems we are working on is categorized as transition issues. Okay. So for example, we're working a lot in farm to automate different farming operations, right? Spraying, mowing, all those things. One of the toughest problems is how we make sure then we don't run off a human in the farm. Okay. Guess what? That is a transition issue. If you fully automate the whole farm, you won't have human. You know exactly everything that exists inside that farm, right? But because of this transition issue, so much effort now is spent on just tackling that. Okay. Same thing with self-driving car, which I'm going to talk a little bit more later on. If every car out there on the road is self-driving, the problem is much, much simpler. Much, much simpler. You still need to handle pedestrian, yes, absolutely. But the whole set of problems is much simpler, right? So, but right now, so much of our energy is spent on handling this transition issue between the way we're doing things now to full automation. There is a transition period that is actually making this thing much, much more difficult in many, many industries, actually. Finally, my advice is if you guys start a company to develop robots for different things, involved in robot development, bottom line is developing great robot is tough. There's a lot of groundwork that needs to go into it. Just because you can demonstrate the capability one day, oh, it works fine. Okay, that is so far away from the finish line, right? So just hang on and push forward. It can be done. Okay. So where do we go from here? Okay. So we are in very interesting time right now. So this is a chart I put when I gave a talk recently. Okay. So again, we've been doing this for about 20 years. And what we notice is the past couple of years, the pace of innovation in terms of software progress, like machine learning, hardware, and everything else is increasing. Right? The curve is increasing significantly. Before you see improvement, little bit improvement, little bit improvement. The last few years, the curve has been much, much steeper. Okay? So then what happened is, if before we can only address the higher cost and high margin industrial robot, now we can start addressing the high value added premium robot. For example, you can buy a $1,000 robot to vacuum your house, like $1,000 robot. Right? It's very expensive, right? But many companies build that, iRobot and other companies. Okay? So, and as you ride the curve even higher, then at some point, which I think not that many years from now, you will start seeing mass adoption of robots for every market. Okay? Industrial, retail, household, and medical. Okay? And the thing that makes this thing all possible is at the same time, the cost curve is going down. Right? It's a positive feedback loop. you find more application. It increases the supply base. So the component is produced at higher quantity. Okay? So drive the price of the component and the robot down. As you do that, it opens a whole new market, new application, new robot, and in turn, it increases the quantity, and you get that positive feedback loop, right? So that's what we've been seeing. All the cost of the component keep going down, capability keep going up, and that's what make it interesting. Okay. And because of this, one trend that I think will happen faster and faster is the whole industry, robotic industry, move away from vertically integrated industry to more horizontally arranged industry, right? Right now, if you look at a robotics company, they tend to do everything. They tend to build the robot, they tend to build the mapping software, they tend to build the positioning software, they tend to build the user interface. And that's a sign of an early phase of the industry. Okay? As the industry matures, you will see a set of companies out there that will provide a mapping solution. Okay? So if you want to build a robot to clean this room, for example, you might build the scrubber, but your mapping solution you just buy from a supplier. Okay? And same thing from user interface. Same thing for machine learning. Okay? So this is a sign of maturing industry, and I think we are seeing the early phase of that. And there's probably a lot of business opportunity actually in that aspect. There's not enough supply chain in this whole robotics ecosystem that need to be there. Okay? It's just not scalable for every company to build their whole vertical stack. Okay? So now on that note, just a couple of comments on self-driving car, okay, which is certainly one aspect of robotics that is maturing pretty quickly. Okay. So certainly there are still some serious challenges left, but I think I'm optimistic they will be solved. I think in general people feel they will be solved. Okay. One interesting thing is, a lot of money is being put in right now, billions and billions and tens of billions probably. Okay. But probably like anything in automotive, once the capability is there, probably will be commoditized quickly by all the tier one. Okay. Most car company doesn't develop technology, right? They buy camera from Bosch, radar from Continental, ultrasonic sensor from Valeo, and maybe CPU from NVIDIA, right? So one thing we might see is as soon as the capability is proven, they are going to go down, hopefully, pretty quickly in the cost curve there. Okay. One interesting thing is, this is one of the perennial discussion topic, philosophical topic, right? We car manufacturers differentiate themselves with safety features, okay? So if you buy a 4.4, they might say, hey, we guarantee it, however we make a decision, the computer make decision, we keep you safe. We crash into pedestrian before we crash into the tree, right? And another car manufacturer said, no, we're not going to do that. It's interesting which car you want to buy, right? You might be rewarding the bad actor. You might be rewarding the car manufacturer that bias that safety setting for the occupant of the driver, right? And there are other pros and cons, right? The great thing is, my definition of where self-driving car will be good enough for me, for example, to buy is when I can take a nap in it. I can go inside the car and go to sleep. If I cannot do that, then I don't know, what's the point? I mean, you have to watch it driving, and I mean, it's not fun to do that, okay? So, but if the car can be that good, most people will get 1-2 extra productive hours in the day. You can nap, reading, play with your kids, or you can waste more time on Facebook if you want. Another great thing is, despite the hiccup, some accident that we're going to see, my belief is that we deploy more of these things, there will be more accidents. It's just part of the process. But overall, it will reduce traffic fatality. There's no question about it. Okay? Allow car sharing to be much more practical too. Okay? Now, if certain things happen, it could be much better for the environment. But this is not a given. I will go into that. Okay? And also potentially reduce the cost of transportation. On the other hand, not so great. I don't know. Personally, I found the 1-2 hours of driving I spend every day is one of the few quiet time that can really think. I mean, I think some great idea when I'm driving, especially long distance drive, that you lost, right? Suddenly you replace that with a screen time, probably, with your iPad or your phone. So Not so great because now you don't have to drive. People can live an hour, 2 hours away. You can live 2 hours away from Pittsburgh. Who cares? You know, you can sleep in your car, right? So this might increase urban sprawl. And instead of reducing resources, you're using more resources. Because people can just live far away, and who cares? I can have a nice property 2 hours away in the mountain. I can get to the car, press a button, and be in the office 2 hours later. Okay? And depending on the cost, if the cost is high and not affordable, then it will bias, you know, where of people having all this productive time, additional productive time, not so much for the less fortunate people, right? And that might not be good socially. Another thing is, again, unintended consequence, right? Right now, if I want to go to eat a nice meal downtown and I cannot find a parking space, well, too bad. If you have autonomous car, they let you go in front of the restaurant. You just tell the car to go around the block forever. I mean, go around the block forever, and they pick you up after you're done, right? Imagine if everybody doing that. I mean, everybody doing that. It's crazy, okay? Which brings me up to, if we are not careful, one of my predictions, hopefully this is not true, that everybody will have a Winnebago, okay? Because why, you know, American especially like big stuff. We have the biggest house in the whole world, you know, per capita. We have the biggest car in the whole world per capita, right? The reason why we all don't drive a Winnebago is because it's terrible to drive. It's hard to drive, it's hard to maneuver, but who cares? If a computer drives it, who cares? Okay, who cares? 100K and you can have your living room, right? In the morning you go there, in the 1 hour commute to your office, you can sleep, you can exercise, you can shower, you can do whatever you want. You can play with your kid, right? So what will prevent this future from happening? I'm not quite sure, you know, maybe you should tax how much of square feet of road you occupy and multiply by the time you're occupying it, you know. Because otherwise, what preventing 1 million people from buying a Winnebago and make the road their house, basically, right? You just go around and around and around. So anyway, there's a lot of this complex thing on this self-driving stuff, but certainly it will be a pretty interesting future, actually. Okay. Now, separate from self-driving car, you know, where do I believe sort of the robotics technology is right now? Okay, I believe right now, as the technology stands today, you know, industrial robot, service robot with unit cost of 50 to 150K is probably the sweet spot. It's very, very doable technology-wise in many industry. Okay, we can operate that within a dynamic but well-defined environment, factory, warehouse. Even for self-driving car, probably the first application is in geofence, so like downtown Pittsburgh, right? There's a lot of people there, a lot of moving vehicle there, but it's well-defined. You can build a model of downtown Pittsburgh. Okay. Another thing is application that allow graceful shutdown or pause. Okay. This is what makes certain things much harder. For example, you have a drone delivering packets to your home, Amazon drone. If it's flying above people's house and you detect a fault, you cannot just stop and crash to people's house, right? But in many applications, you could just slow down and stop. So those are much easier to address from safety perspective. And finally, the things that is still hard is having a complex interaction with human. Okay? If you think the way you interact with your coworker, with your family, the big difference is you can interact with them in very cognitive load. You know, you can just talk to them, converse with them while you are typing something on the computer, things like that. That is not the case yet with robot, right? You need to put a lot of cognitive load to interact with them. This is why I think currently the application that just requires simple interaction probably is still the key there. So what's next, okay? So if you fast forward 5-10 years from now, I think what we are seeing is computer vision and smart camera will become ubiquitous and basically free. Even now, it's amazing what you could build if you build it in China, for example, what you can build for $10, $20. You know, a nice camera with a pretty nice processor that can do amazing things. You know, CNN, deep learning, everything, right? I think in a couple of years, that probably we get reduced to a couple of dollars. And after that, probably below $1. Okay, so when camera with all the intelligence behind it, cost less than $1, the application will just booming. You will see camera everywhere, basically. Same thing with display, right? Head-mounted display, AR display, virtual reality, all that, e-ink, all this display technology. I think we are at the point where it becomes ubiquitous and also free. So there's no more sense of having a wallpaper. Why you have a static wallpaper instead of OLED wallpaper, you know, which bring up interesting opportunity, right? Same thing with computing power, you know. I mean, most of you guys are too young to remember the 1980s, 1990s, right, with the 9600 baud modem, you know. It's from 9600 baud modem, now we can get with 5G, you know, 96 megabit. I mean, the amount of bandwidth increase is staggering. Same thing with computing power, okay? So this will become free again. And then when we combine that with progress on electromechanical, that's when robot will become popular, right? And my prediction is at the price point where you can lease a capable robot for about $499, $999 a month, the adoption rate will skyrocket. Who doesn't want to have a robot at your home that have cleaning, pick up the dirty laundry, putting it in the washer, push your lawnmower, right? Everybody would want one, okay? But it needs to hit that price point, right? And it's not a purchase thing, it's lease, okay? So I think this is the sort of, in my opinion, the magical price point for household robots. So on the display, right, just an example of combining display and camera, right? So I was looking to replace my window in my house lately, and I look at the cost of a double hung window, and find out it's like $400, right? And I also just buy a TV, same size, it's like $400, right? It's like, how can that be? I mean, just how can that be? One is so complex, okay? One is a piece of wood with a glass in the thing. Right? So how can that be? But it's true. You know, I bet in no time at all you could have a virtual window which is cheaper than physical window, and what will happen is, you know, you can have virtual window with Hawaii, right? And with the camera tracking technology, it can track your motion, so the perspective will change as you move around the house, okay? Or you can have a virtual share wall with your grandmother. Your grandmother lives in Asia, for example, right? With the 5G bandwidth, with the camera technology, you can have one wall fully lined up with display where you see the living room of your grandmother. And you just see her moving around, and she can see you moving around too. Or you can make it one way. So I think this future actually is coming very, very quickly. You know, it's actually pretty scary to think about it, but it's moving very, very quickly here. Okay. Another example is, you know, this is a video of a virtual reality system we are augmented reality system we're developing for the Army. The Army would like to have X-ray goggle basically for their soldier. So they can wear this goggle, they can see explosive landmine that is buried under the ground, right? So what we do is we take a radar detector there, and we map the output into an augmented reality goggle so he can see that thing. Usually that round thing is buried. We just put it on the ground so you can see it, okay? So they really love this thing. We are developing the 3rd generation of this. But you could imagine, okay, what the future looks like, right? You know, you live in Pittsburgh, the weather tends to be cloudy. Once the augmented reality goggle is good enough, you can press a button and it becomes sunny, right? You know, if your wife or your husband get tired looking, you know, at you, he can press a button, and now I become like a Brad Pitt, right? You know, with one button. It's actually not that far away, you know, face tracking. And the Brad Pitt face could be animated with as you talk. It's all there, right? It's so and then like in logistic, right? Everybody here probably has Amazon account. Right now, by the time you press the click there on the Amazon web page until your order show up on your door, many human is involved in taking care of the packets, right? I think the technology is quickly enabling what I call zero human touch logistic. Basically, from the point you click order something, that order is fulfilled in the warehouse, put in the truck, put in the airplane, unload it, and carry to your door. We involve zero human touch, actually. I think this is, of course, what everybody wants to happen. And it will actually happen probably quicker than we think. Okay? So anyway, so my message is this is an interesting time. We are in a period where many things is possible. Okay, so you guys, I encourage you guys to dream big. Okay, not only dream big for obvious application like self-driving car. Okay, I encourage everybody to dream big and apply some of this technology for something that might be more beneficial for like humankind. There's many things that could be automated that might benefit the environment, for example. Okay, but we need to be imaginative about that. But it's time to dream big. And finally, okay, we still need people. Okay, we built robot, but we still need people. So any of you guys who might be interested in getting into robotics or know somebody, whether in the US or outside the US, who want to go to the robotics, good engineers, please contact us. Okay. Anyway, that's all I have.
Okay, questions? Yeah. Take your questions.
Okay.
Did I hear you say that the computer vision problem will be solved in 5 to 10 years?
I think for many applications, yeah. I think in many applications that we can use almost on daily basis. General probably will take longer, but my argument is to be useful, the 80% thing probably, yeah.
Most of the problems that will be solved are hardware problems. What about the software problems that we're currently solving?
That's a very good question. I think we need to work more on automated tools for the software. Humans just make too much mistake. Okay? And I think actually one of the value in machine learning is not just machine learning, it's the fact that you remove a lot of programmers' effort in hand coding all those algorithms, where you can introduce mistake because training, you could structure it better, you could think so. They might reduce software bugs actually. Okay. But yes, software is still a big aspect of this thing. Right? The two go hand in hand. Yeah. Yep.
You said that robotic technologies are becoming cheaper. Do you know why that is?
Yeah, it just some of them are driven by other market. Like the cell phone that we all use, the smartphone we all use, drive down the cost of camera imager because now they are built in billions quantity, right? And the robotics market itself is getting larger. And it's getting larger, you got the economy of scale. So before, a laser manufacturer produced 100 units a year and cost 100K. Now they produce 10,000 units a year, and the cost goes down significantly. Okay. So, any other questions?
I have one.
Okay.
Nobody else. So there is this idea, this is sort of like the rebels in technology, the Luddites among us, who are saying that self-driving cars driving in a place like Pittsburgh, with traffic, with pedestrians, with animals, all of this, right, is basically equivalent to the general problem of artificial intelligence, right? So I'd like you to take a stab at why is it or not, you think? Because if it is the problem of it's the general problem of AI,
yeah,
then we're doomed.
Yep.
Okay.
Yep.
They spent a lot of money.
That's right.
Built all these wonderful restaurants in Pittsburgh.
Yep.
Okay. To feed all those techies
Yep.
who are working at Uber and elsewhere.
Yeah.
Okay. So we appreciate the fantastic sushi and poke in Pittsburgh, but that future is not coming soon.
Yep.
So what's your take?
I think it depends how we evaluate, how we define success, how we define a system that can drive autonomously, right? It's not going to be perfect. I think
it will be, let's say that the system which is cheaper and as good as the Uber operator today.
I think that could be done. if
In a
it,
city like Pittsburgh.
I think it could be done in city of Pittsburgh. If the goal is to have a perfect self-driving car that never hurt anybody, then I agree. It's a very hard to almost impossible problem.
So as
Okay.
effective, as cheap as a
And statistically, have
basically as the
safer.
same accident rate
Yeah,
or better.
yeah. Because humans are not,
That's,
yeah.
that's happening
Yeah, yeah.
anytime
Yeah.
soon. Like what? What's your prediction? When? Like it's
I would
not-
say in about 5 years time frame.
Okay.
I would say in about 5 years
I
time.
get asked this question all the time. And, I'll
that's
just say from now, Herman said it.
5 years.
Either you get 5 years or 50. So there's nothing in between.
There you go.
That's right. That's a good point. Okay.
Other questions?
Okay. Well, thank you.